Alright, last problem, and then I can finally go to bed. Oh no! A bear is chasing you towards the bank of a river. The river is 50 feet wide, and the safety of your car lies 100 feet down river on the opposite bank. You're able to swim through the water at a constant speed of 3.5 feet per second, and can run on land at a speed of 15 feet per second. Draw and label a diagram that represents this situation. Hopefully, you recognize this problem by this point. So let's go. There's our river. Oh, okay, awesome. Our river's pink. I meant to hit blue. Whatever. We got a pink river. So there's our river. Let's say here. Let's say that is you at the bank of the river. You've run to the bank of the river, and now you're trying to figure out how to get across it and how to get to your car. And so let's say this is your car. And what are we told? We're told that the river is 50 feet wide, so that means directly across from you. Let's call that point B for maybe the bank of the river. We know that like that distance right there is 50, okay? And what else we know? We know from the car to point B is 100. Is that what it says? Yeah, 100 feet down the river on the opposite bank is your car. So we have that situation, right? And so we have this little triangular diagram. That doesn't look like a triangle, does it? Yeah, it is. It's a little triangle. Imagine like you could swim like that and you can go straight to the car, right? Or you could swim straight to B and then you could run to the car. Or you could land somewhere in the middle. And that's where this problem comes to life. So we're going to say we don't know exactly where we want to land on the opposite bank. Somewhere between B and the car. Either at B or at the car or somewhere in between. Those are our only options. It wouldn't make sense to swim past it because that would definitely not be the shortest distance. So let's label things we know. We know this entire distance there is 100. And we don't know where we're going to land, so we need to get a little generic with this. We need to generalize things. Let's call this distance between where we land and point B, let's call that x. If that is x, then that means that this distance right here has to be 100 minus x, because we know from car to B is 100, so if we've gone x up from B, then that has to be 100 minus x to get us back to 100 if you add them together. Okay, well, what else do we know? Well, we can figure out this distance with a little Pythagorean theorem. You should end up with the square root of x squared plus 50 squared. And so we have a couple pieces. We have this 100 minus x, which represents your distance on land. And we have this square root of x squared plus 50 squared coming from the Pythagorean theorem, which is your distance in the river. And we want to know what should that value of x be if we want to minimize our overall time. And so we need to come up with a time equation. If we want to minimize time, we need to come up with a time equation. So how do you find a time equation? Well, we know the distance based off of x of each of the pieces, and we know the speed we go based off of which piece we're at. And we should know that distance equals rate times time. And if distance equals rate times time, then time has to equal distance divided by rate. And that's the fact that we're going to use here. So if we want our overall time, it's going to equal the time in the water and the time on land. So the time in the water is going to be our distance in the water, which is the square root of x squared plus 50 squared, divided by our rate in the water, which we're told is 3.5 feet per second, so over 3.5 right there. That now is distance in water divided by speed in water. Distance over r equals time in water. And let's add to that our time on land, which will be our distance on land, 100 minus x, divided by our speed on land, which is 15 feet per second. So now we have distance on land divided by speed on land gives us time on land. So our time equation, t, tells us the time. Yeah? Okay, cool. So here is our part A. Here is our part B. And now let's do part C. What is the minimum amount of time it takes you to get to your car? Well, that is a calculator problem at this point. So on your calculator, we need to graph this. How do you find a good window? Well, think about it. Think about x values. If I went straight to B, x would be 0. If I went straight to the car, x would be 100. So x min should be 0, x max should be 100, and then just do a zoom fit, and you should get a pretty graph. Alright, so again, if you have a new calculator, you're lucky, and you can type it in a way that makes sense, and it looks like it should. If you have an old calculator, then you're not quite as lucky, and you have to type it in a really gross way that looks like that. But hopefully you're used to whatever calculator you have, and you use parentheses if you have an old calculator. So there's that, and we said window. We're going to go from 0 to 100, and then we're going to hit zoom 0 to do a zoom fit, and it's going to give us a perfect window every single time. So you should get a graph, and it should look like something like that, where you can see a little dip, and then it rises up and goes up. So second, calculate minimum. Left bound 0, right bound 100. Enter, enter, and it tells you that the x value is 11.997 and our y value is 20.558. And remember, y is essentially the same as t, right? Because we graphed y equals square root of stuff. And so y is t. And so the minimum time to get there is 20.558 seconds. I hope that's enough time to not get eaten by a bear. Bye.